All right, AP Calculus, lesson 7-2, motion integration. We're going backwards today. Yesterday we went forward, taking the derivative. Today we're going backwards. That's what it's all about. Today's date is Tuesday, January 7th, 2020. Who wants to read the objective? A yawn again from Geo 2 days in a row after I asked for the objective. Since your mouth is nice and stretched out, you're ready for the objective, Geo?
Explain the meaning of the integral and find its value by hand and with the calculator.
There it is. All right. So I always want to make sure that you know how to do both versions, right? Almost half of the AP test is calculator, half of it is by hand. I will make sure you know how to do both. And there's some good calculator practice in there. So say we have a graph of velocity. Again, units of some units per some time, not per time squared, notice. And we have not an x-axis, a t-axis down here. It is just a constant graph. I want to know how much the position is changing between time 1 and 4. Not 0 and 4, but 1 and 4. So we always do the default. We come back here. We make our lines, right? If you want rulers, now is probably a good time to grab those. We have our lines between 1 and 4, and we say, okay, well, what we're really talking about is the area underneath here, and you can find the area 1, 2, 3 by 1, 2, 3, 4, and you say, hey, that area is 12. I'll wait for you guys to catch up. Today, I get to be a little bit more formal. I've always talked about these infinite number of rectangles that's actually happening. How do you actually count up 12? What if this was a curve? What was Isaac Newton really doing when he was talking about the integral? So in your mind's eye, or if you want to add it to your notes too, you want to think about an infinite number of infinitely thin rectangles, which sounds like a contradiction, and it is, right? The only reason that we have a way around this contradiction is by applying formal calculus. I mean, back even with the Greeks, they're thinking about what happens if I do an infinitely many, if I take an infinite number of smaller and smaller infinitely steps, but I have an infinite number of those, do I actually get somewhere? And it's a contradiction. And you have, what's up, Arrow?
No, I just realized what you were talking about. I understand now. Okay.
Like you have there's Archimedes and the tortoise, there's the bow and arrow. You can think about these classic riddles as if I shoot an arrow to a target and the arrow is traveling. In half of this distance, it travels this speed, but then if I look at the next half of the remaining distance, I'm always looking at half the remaining distance, I'm traveling less far, half of that remaining distance is this far. Do I ever actually hit my target? And well, you're like, I've shot an arrow before. You do hit a target, but mathematically, if you're always traveling half and then you're talking about the distance, you kind of seem to never really get there. And it's this weird contradiction. It would be fun to just spend a whole day on that. My first year of teaching calculus, I spent a whole week covering them because they're kind of fun and interesting. I didn't realize that yeah. Anyway, so you have an infinite number of these rectangles. What do those rectangles look like? So I'm going to come down here and we'll have some free space. We'll actually do the full-on calculations up here in a sec. I'm maybe going a little bit out of order. Go ahead and draw a rectangle. Let's treat this as a fat rectangle. I know it's supposed to be infinitely thin, which means you can't really see it. I'm drawing let's do a red or black rectangle with no fill. Say I have some rectangle that looks like that. What do these infinitely thin rectangles have in terms of their units? Well, I know that height is velocity. It says anything that has a point here, this point, this point, this point, technically this point on that line, all of those points are velocity, units of feet per second, right? So I can think of this left-hand side having units of feet per second. Well, what is this other dimension, this dimension right here? Well, that's how much you've changed in time. It's basically zero time, but I'm going to call that the change in time. Anciently, it was called delta t, like that. I'm going to call it dt. It's the more modern definition, the change in time. Delta just means change, right? It's funny that my English teacher is still the first person that ever taught me that word instead of my math teacher, because she would always write on my papers like delta your sentence structure or delta this word. You need to change these things. My math teacher should have been better. I don't know. Maybe my English teacher was really good. But there it is, my delta t. When I multiply these things together, and what is, by the way, change in time, therefore my unit is time. Or seconds, yeah, you're right. Seconds. So I have something that's feet per second times seconds. So my unit, my area for this rectangle, you just multiply them together, you get, yeah, feet per second, and then I'm going to multiply that by my other unit, which is seconds.
So it's feet per second squared.
Well, no, because it's not on the bottom. They cancel out. This has a unit of feet, which is weird, right? You're like, area, doesn't area have feet squared? No, in calculus, when I'm going backwards, this is now an area of just feet, an area of displacement. How far have you gone? You've gone this many feet. This area here represents how far you have traveled. If I add up an infinite number of these infinitely many rectangles, I have now calculated an area of how far you have moved.
Does that mean that the curve that this rectangle is under is velocity?
It does, yes. The V there for velocity, feet per second. So this is an area, and this is a unit. I'll put over here. A unit we use for position, a unit of position, I guess. So what are you really doing? Well, obviously you're doing one thing. If I take the, this is kind of my scratch work. I'm just freeballing here. If I take the integral of velocity, integral of vt dt, I get back to position. This is equal to x of t. Or if you want to put underneath this, you can say velocity, the integral of velocity is equal to position. That's not quite true. It's the displacement of the position, how far you have changed. If I did this exactly, it is the exact position, but we don't know the starting conditions. So what we're really finding here is the position change.
What if we had an integral with like bounds? It would be position?
It's still position change. The only thing that will change it from position change to your actual, like, where are you? What is your actual location over is where did you start? If I have my start and then I add the change from that start point, now I've figured out exactly where I am, my actual position. But that's a kind of a key point, and it's going to be hard to distinguish those two. And this is an AP concept that is going to be tested. What is the difference between position and position change? All we're doing right now is the change in position by finding this integral. So I'll eventually rewrite this stuff down there. I'm just kind of doing the building blocks. Let's come back up here. So what am I really saying by writing this now? I'm doing the integral from where to where again? From 1 to 4, so I'm putting those on my bounds, my integral, of vt, my velocity dt, with respect to time. Okay, eventually we're going to need to calculate these integrals by hand, so I'm showing you where that comes from. Eventually we'll do an example problem. Well, the integral of velocity goes back to
Position?
position, yeah, and then what function is position? Is that x, y, what are we doing here?
X.
We'll do x, sure. That's equal to x of t. But because it is a definite integral here, I need to have an evaluation bar. I don't know what happened there. Go away. Why is it not going away? I have to have an evaluation bar between 1 and 4 because I have my bounds. And then I plug those in. Whenever I have evaluation bar, it says, hey, plug that in. This is now equal to, I plug in 4 first, and I subtract whatever happens when I plug in 1. Well, what is x of 4? What is the height at 4? Well, we don't know. We just know that is your position at 4. So let me label these things because this is important. This will come back in about, I don't know, 5 minutes. This is the position, not the displacement, but the position, your actual location, your position.
Because we know where we started.
Assuming that you know where you started, yeah, at t is equal to 4. We have to assume that. And this x of 1 is your position. Ran out of room. Position at time is equal to 1. If we knew those things exactly, then we would be able to answer the question. Unfortunately, I haven't given you enough information. We don't know those things. Those are just variables to us. If I somehow knew my exact position at 4 and my exact position at 1, then I can subtract those things, and that is the integral of velocity. Connect that with what I just said. I just said, when we take the integral down here, that is the change in position. Well, look at that. Subtract one position from the other, that is the change in position, written a different way. One position, and I subtract the other, the difference there is the change.
Okay, never mind. Good.
I know I'm getting very conceptual, and you're like, okay, how do I solve problems? I'm not quite there yet. But we do know that the change in position, this problem is 12. So let's go ahead and, I guess I should really be moving this up, because this whole topic was why the derivative is feet. So I'm going to make a note for myself as a teacher. This needs to be moved up to right there, because that's what I was talking about. Why is the derivative of feet per second equal to feet? Well, yeah. Okay, so let's talk about this. This is the formal definition. This is the thing you're going to be writing over and over again on the AP test. If I have the integral, the definite integral between a and b of velocity, that is the total change. And I'm going to write this in red because it's the most important thing I'm probably going to be writing today. This is like a point here. If you remember this, it is a point, and you know how to apply it. Total change. And I'm going to underline that part. That's the key part. And then this one is also kind of important. I'll do yellow, I guess. In position. And then you need to have the third part as well. From A to B. So, in terms of what's going to be the same, you are always, 100% of the time, going to be rewriting the red and rewriting the blue. You need both to get the point. This is the hard part to memorize. Well, it's obviously going from A to B. It's not as important because you'll memorize it. You have to rewrite total change in something. If I'm integrating velocity, I get back to position. If I integrate acceleration, I get back to velocity. So I could say the total change in velocity if this was an A. From A to B again. But you have to have that keyword, the total change in whatever the correct unit is. Position, velocity. I'm not saying that quite right, but I think you guys get it. So there's a tiny tidbit on finding average velocity. There's random questions that says, find the average velocity of blah, blah, blah. And this is how you find it. So you need to find the total position. Total position. Or I guess the total change in position, if I'm being exact. Total change in position. Then you need to find the total change in time. And step 3, divide them. Done. That's it. AKA delta position over delta time. So one way to think about that, there are two equivalent things. So I can say it's the change in position over the change in time. Or I can think about this as the change in position. We have a formula for that already, right? The change in position, I can either think about that as the integral of Vt divided by t. So I can think about it as two ways. I guess I should have really 3 equal signs. I should think about it as the integral between a and b of Vt dt divided by the change in time. Well, the time, remember, all the way up here from the beginning, between time 1 and time 4 and time 4 were parts of the bounds of the integral, which means my time is right there. 1 and 4 are the time, which means my time on the bottom is right there and there. Just do b minus a. I would say 25 to 40% of the time on an AP test, they will ask you the question, find the average velocity of blank. The only difference between average velocity and the total change in position is this. It's the same integral, total change in position, except now we're dividing by b minus a. It's almost the exact same thing, except now we're dividing by time. And if you're very clever, you might relate this all the way back to Unit 1. You're like, wait a sec. If I do this again, this integral from a to b of Vt dt, we've written down the definition. That's x of b minus x of a. So if I come back down here and rewrite that same thing, this is x of b minus x of a. And I'm going to leave the denominator the same. The denominator is still b minus a. Does anyone get a lurking feeling that they've seen that before?
It did seem familiar, but that's.
Does anyone know what that is?
It's this.
It's slope. That's just the average slope.
Mhm.
Whenever they ask for average slope, you're really finding the average velocity. And that makes sense because slope is the velocity.
Yes, that does make sense.
So it's all coming together, seeing multiple connections. That's what math is all about. Let's see an example. This is totally new from last year. I totally made up these problems. So Arrow has never seen them before. Mwahaha. I'm trying to make my notes better and better. Say I have a random table. The important thing to take away is we're dealing with velocity. That's the only thing I'm really taking away from this table so far. Explain the meaning of this integral. This is an AP question. They say, hey, what does this mean? Interpret. And you will use these key words that I've just said right here. Okay, well, I know it's the integral of velocity, so this is going to be the total change in, okay, we were with velocity. Integral of velocity, is that going to be velocity, acceleration? Is it going to be position? What am I really talking about here? Position. Total change in position. From where to where? You do need to have the units.
0 and 30.
From 0 what? From 0,
30.
0, what are our units for our time? From 0 seconds to 30 seconds. You have to have the units on here. You will lose the point on the AP test if you just randomly forget the units.
If you write from 0 to 30 seconds, does that?
That counts. Yeah, you're distributing the units into the 0 and 30, right? Done. That's the answer. You just got a full point just by writing that.
That's it?
Yay.
That's it. Done.
Okay.
Let's go on to part B, which is the hard part. How do I calculate that by hand? Well, we have this fancy formula right here. You just take the position minus the other position. And let me fully derive where this comes from again. What we're really doing is we're taking the integral, the definite integral of velocity. So this is equal to, I'm just going to, not even rewriting it. Well, what is the integral of velocity? I go back to what function? Position. So it's going to be x of t. And now evaluation bar, because it's a definite integral between 0 and 30. And that's going to be equal to, well, I plug in 30, and then I subtract what happens when I plug in 0. So it's going to be x of 30 minus x of 0. This is that rare time that they actually gave us the information, hey. Oh, did they? Now I'm confused. Because they didn't give us the position.
Oh, wait.
Did I mess up in making this question? I should have been giving you position here. Oh, okay, I know what happened. I should have been making this a three-way table. Okay, so let's add on to this table above it. I'll fix this for next year. This is what happens when you do things for the first time without running through the notes. This should be a table with 3 parts, where this upper part has units of x of t. And I should be giving you values like, let's make them easy, 0. They have to match up roughly. 0, negative 10, let's say 15, and it doesn't really matter what I put over here, so I'm just going to randomly put 47. So now I have given you the information that you do need. X of 30 is what?
X of 30 is 15.
Is 15. So this is equal to 15 minus x of 0. What is x of 0? 0. So the answer is 15. Don't forget your units. Units, units, units. They will give you, they'll take away 1 point if you mess up units anywhere. Well, what are we dealing with here? What is x? Position. What are the units of position?
Meters.
Meters. Done.
Wait, where'd you get the 15?
This 15 came from this 15 up here in the table. Yeah, good question. All right. An example without a table. This one I am more confident in. So I have a position, and it has this equation, 6t squared, for the position. Think of this as the position. Position is 6t squared. I know the exact position. Not the change in position, I know the exact position. But I need to figure out what the average velocity is. What is average velocity again? You should know this now. It's kind of one of those, memorize this. You can think of it as slope. So you can think of it as x of my last number, x of 5, minus my x of 0. All of this divided by 5 minus 0. But how do we get x if we only have, oh, that is position. We just need to plug it in then. This is essentially saying, hey, x of t is equal to 6t squared. So how do I do x of 5? We'll plug in 5 into 6t squared. 5 squared is 25. If I have 6 25s, if I have 6 quarters in my pocket, I have $1.50, so I have 150. This is now equal to 150 minus, when I plug in 0, I get 0. All divided by 5 minus 0. What's 150 divided by 5? 30. Don't forget your units. This units can be a little bit confusing though. What are we really talking about here? It's the average of what?
The velocity, so
It should be units per time. And I didn't really say what that is, but I'll say units per time. Many people, I've had a lot of students, even though I haven't had very many students, a high proportion of students say, oh, well, look at this equation. It's an equation with position. No, it's talking about velocity. It's talking about average velocity, so it's units of velocity. And again, if I were deriving that full equation, I would have been writing, well, it's really 1 over b minus a times the integral of vt dt from a to b. That's really where this is coming from if you want to rederive it. It's coming from this thing that I just did up here. From here to here. That's what I just rewrote. Know that average velocity is integral of velocity divided by time. Or if you want to think about it a different way, it's just the slope. Go back to slope for average velocity. All right. And then finally, calculator question. Calculator's out. A 150. So x of 5, I plugged in 5 into this formula that it gave us. 5 squared is 25. 6 times 25, 150. Calculators. Get them ready. Let's read this question. We know the velocity of a particle, I think. Yeah, velocity of this particle is 4 natural log of t plus e to the power of 2t. Well, that's why it's a calculator question. It's freaking hard. Okay, so let's do this. What is the average velocity of the particle? Oh, what's average velocity again? It's slope. But in this case, we have to go back to the original definition because we don't know, we can't punch in what the position is. They only gave us velocity. Since we don't have position, we're using the thing that they gave us, velocity. So I'm going to rewrite this 1 over b minus a integral of a to b vt dt. I'm going to be filling in this formula. So this vt, we know that's 4 natural log of t plus e to the power of 2t. B and A, we're talking about 1 and 2, so A is 1, B is 2. We need to basically, on our calculators, somehow type in the integral between 1 and 2 of that function 4 natural log of t, I guess, and it's going to be x on our calculators, plus e to the power of 2t, all that dt, all that divided by 2 minus 1, which is 1. So I don't really need to do the division in this case. But still, how do I do an integral on my calculator? First, I'm going to show it with the new calculators, then I'm going to show it with the old calculators. It's opening slowly. Okay. Yes, yes. Okay. So, on my new calculator, I'm going to second quit out of this. That was stuff from yesterday. So, first, I go to the y equals, and you can do this on the old calculator as well. I'm going to have to retype it really quick. Okay, so retype 4 natural log of your variable and the parentheses plus e, so it's going to be second natural log. You have to hit second ln, second natural log of 2x. Okay, so I have that equation. Let me come over here and do it as well. This is going to be, it'll look a little bit different too. So it's going to be 4 natural log of your variable plus second natural log e to the power of 2x. Okay, so that's what it looks like on both calculators. We're all okay.
Where's it? E?
E is second natural log, second ln.
Oh. Okay.
All right, so we have that. Let's go second mode to quit out of it. Second mode. I don't know. Okay, so now we're at this screen. We're going to go Math 9. Math And then you can see 9 is F integral. Math 9 there. Come over here. Oops. Get out of this. Math 9. So the integral. And then on the New York calculator, it's pretty straightforward. It's between 1. Did I just hit? What's going on here? Between 1. What? What is going on? I don't know. Is it? It's just catching up with me. Math 9. 1. I go to 2. I do vars right, enter 1. My calculator is running slow. It's probably because I'm recording. Let's come over here. This one runs a little bit better. This one's going to be math 9, and this is going to be my vars right, enter, enter, my y1 variable with respect to x from 1 to 2. And then you should get an answer. Let's come back over here. Hopefully this one will work. Why is it not working? You calculator, you. Well, that's not good. I was planning on using this calculator for the entire year.
Maybe it just needs to be updated.
Oh, that's why it keeps coming up.
Yeah.
Okay. Let's try it one more time, and then I'll try to do this off camera, I guess. Vars, right, enter. No! Oh, there it goes. Vars, right, enter, enter, and dx. Enter. Please work, please work. It's just running a little bit slow. You got this. Someone with the new calculator, did you get 25.14, I guess 150?
Yeah.
Yeah.
Because you have to round it correctly?
I just did the weird like cutoff thingy instead of rounding.
Okay, so that will, yeah, both of those answers are correct. You truncated. I'll leave that up. Okay, so yeah, the answer here, without further ado, was equal. So you should always say approximately equal to if you're being precise, but you're not going to lose any points. It was 25.150. 25.150.
And do you have to include the 0?
You
Just do 25.15.
you won't lose points if you just do 25.115 because they know that you rounded. I highly recommend just getting in the habit of always doing 3 decimal places. That way when you look back, you're like, oh shoot, I rounded incorrectly. No, you did it right. You just knew that it was a 0. That's all I have for the notes. The end.